Yeah, it's a little early, but who cares? Does anyone
That
have?
transition though.
No, I know. Does anyone have any questions from homework? I had some good ones earlier. Also, the quizzes have been graded, so if you haven't taken a look, do so now and let me know if you have any questions. There might be somebody, let's see. Well, I'm going to wait and see if I get any questions. I'm not going to bring up anything weird. Okay. Let me see. So one thing we need to do last time, so no questions at all from anything. No questions from quiz, no question from homework. Is that what's happening right now? You guys are all good? Okay, all right. I don't believe you, but we're going to pretend like that's true. Let's see. So last time we introduced the idea of inverse trigonometry, inverse trigonometric functions, right? Inverse cosine, inverse sine. The last thing we talked about was tangent. So we graphed what tangent looks like, and then we talked about inverse tangent. So now let's do cotangent, and then we'll kind of summarize everything. And then we'll start to sneak into chapter 9. Oh yeah. Oh yeah. Let's see. So we haven't graphed cotangent yet. So let's see what that thing looks like. Maybe we should, well, I don't know. Just real quick, just in case somebody wasn't here, tangent basically lives between these two, even though it goes forever. Tangent is sine over cosine. So wherever cosine is 0, there's going to be a major problem. Right? How does that translate graphically? Anybody? Wherever cosine is 0. Sorry?
Wait, what did you say?
Wherever cosine is 0, tangent graph will have what?
Asymptote.
Asymptote. I love it, right? We know that's what happens when the bottom goes to 0. Whatever's not in the domain is going to have a vertical asymptote there, right? Tangent of 0 is 0. Tangent of 45 degrees is 1, because that's where sine and cosine are equal. So same thing happens at negative pi over 4, except they're not the same sign, so now it's negative 1. Let me move you over a little bit. There we go. So it looks cubish. Oh gosh, Jeff. Oh, to be able to graph would be nice. Okay, that's horrible, but it will. So it looks roughly cubish, right? So that's tangent. And it does it forever in both directions. It repeats in both directions forever. This is like the heart of it. So the inverse tangent is going to have a range between negative pi over 2 and pi over 2. All right, maybe. So that's basically what we did at the very end of class last time.
When you say the domain of tangent, do you
Oh,
just
now be
mean
careful.
like skip?
No. Yeah. So what's the domain of tangent? This is a good point. What's the domain of just tangent, purely tangent? And remember, it goes forever, not tax, Jeff. Tangent. So it's here and it's there and it goes forever. So what is the domain of tangent? This is a very interesting question. This is a very difficult thing, actually, to be honest. What is the domain?
You
Can I
just hit like you just skip a bunch, right?
Yes. So for example, so let's kind of start from the middle and work out. So let me move you, get out of the way. So in the middle, it's negative pi over 2 to pi over 2, right? And the next one over would be pi over 2 to what? What's the period of tangent?
Pi.
Pi. So what's pi up from pi over 2?
3 pi over 2.
3 pi over 2. So it'll be pi over 2 to 3 pi over 2. And then the next one down, now of course this keeps going forever, so the next one down would be from negative 3 pi over 2 to negative pi over 2. So it's really not easy to capture the entire domain because it's got an infinite number of asymptotes, 11.
Can I ask you a quick question? So
Yes.
does the domains of inverse function of sine and cosine has like skip domains?
Like this?
Yeah. Or
Definitely not. Definitely not. In fact, we wrote them when we talked about them. We wrote what they were.
yeah, just I thought you can just like
So we have to restrict the domain of sine and cosine to create a function that's invertible.
I was thinking about if you can restrict on the different domains.
Yes, and I pointed that out when we picked. I kind of try to tell you why we pick what we do. It's because it's around 0.
Yeah.
But you could actually pick any section like that in the entire infinite domain, right? You could pick any section like that, but the official definition of inverse sine is built around 0, and the official definition of inverse cosine is built, from 0 to pi, right?
Yeah. Thanks.
Well, that's a cat. Okay, all right. Now, how did we have to restrict the domain of tangent? We had to restrict it like this to make it invertible. Yes, now it would pass the horizontal line test. Before it wouldn't because there was a whole other function here. So if I restrict the domain to just be this, then it becomes invertible. Maybe? You guys still with me out there? And of course, if you
But
miss,
for cotangent, we're gonna limit our window just like we did for
to create an inverse, we have to restrict the
not
domain.
cubic. What's it
Yeah.
called?
All right, hold on. Let's take a look at cotangent because we haven't done that at all yet. Let's do it. You probably should expect it's going to have this shape. Yes, that should make sense. Like cosine and sine have the same shape. They're just offset. So you would think that cotangent and tangent are going to have the same shape. The same way that cosecant and secant, don't they have the same shape? Like this? Cup up, cup down, just offset. Cosine and sine, same shape, just offset. So cotangent and tangent, you would expect them to have the same shape, but they're the ones that decided to be a little extra freaky. So here's what I mean. So cotangent x, let's figure out what the hell's going on with this guy. Cotangent is cosine over sine. So where will his asymptotes? Give me some locations of asymptotes for this guy.
Pi.
Good, pi. Where else?
0.
0. And why does it make sense? What's the period it looks like so far from this?
Pi.
Pi. Which makes sense because cotangent should have the same period as tangent because they are in very many ways the same function truly. Just kind of offset. You can see that. So tangent had asymptotes 90 degrees off from cotangent, which makes sense because they're kind of like based on things 90 degrees off from each other. All right, and then of course there would be another one to negative pi, and it goes forever. All right, it's pi over 2. What is cotangent? Well, of 0 is that? Well, what's cotangent of pi over 2?
0.
0. Now let's think about this. What's cotangent of pi over 4? This shouldn't be that horrible, right? Because pi over 4 is where these are
1.
equal to each other, so it's 1. So what's cotangent of, you could do it, Jeff, 3 pi over 4. So that would be here. What's true about cosine and sine? Which one is positive? Which one's negative?
Cosine
three-
is
Sine
negative.
is positive.
Sine is positive, cosine's negative. So that means, but they both are root 2 over 2, right?
So they're -1.
So it'll be -1, yeah. So it does have the same shape. It's just been reflected. Oh, Jeff. Oh, Jeff. This shit. Oh, crappity dude. I'll make that bigger. Right. It's been, do you see how tangent went like this, of course, and this is going the other way? All right. So it's been reflected, not just shifted, but also reflected. Just because, just to do weird things. And of course, it goes forever. Okay. Forever. All right. So we can do the same thing. We can erase what I just drew. So that was a wasted exercise, Jeff. Good job, buddy. Restrict the domain of cotangent so that it is invertible. So now I'll say it's from 0 to pi. Now, all right. Well, we'll talk about all of the similarities between these things in a minute. I don't know if you picked up on any. What's the range, by the way?
Can you remind me why you did the brackets for 0 to pi instead of the?
Oh, because I made a mistake. That's why.
Okay.
Thank you. So, like, that was very diplomatic of you. Can you remind me why you decided to do that wrong? What's the range? What's the range?
-∞ to infinity.
Yeah. Okay. So for inverse cotangent, that just flips. The domain will be -∞ to infinity, and the range is going to be 0 to pi. All right, so let's do this. Let's summarize what we know about the inverse trig stuff. Let's summarize what we know. So I'll give you a minute to copy down what you want here. All right, I'm going to start to erase and see if somebody yells. Yeah. All right. So what do we know? We know inverse sine. Can somebody tell me the domain and the range? Somebody remember what this was, the domain and range of inverse sine.
0 to 2 pi.
No?
-1 to 1.
Yeah, so the domain is going to be -1 to 1. So remember sine, what did we have to do to make this work? We had to cut it here and there. Remember? Pi over 2. So I'm giving it away. -pi over 2 to pi over 2. And of course, the range here for sine is -1 to 1. So the domain of inverse sine becomes -1 to 1. That's what's so beautiful about inverse shit. Everything that's related to x and everything that's related to y switches. So that means the domain and range just wholesale switch. I remember first learning that, and that was just so beautiful to me. Could just be me. I don't know. All right. Now, what about inverse cosine? So inverse cosine, remember it does the weird octopus thing, right? Yeah. So we had to cut it here to there. So the inverse cosine, its range is going to be the domain of the cosine piece, which is 0 to pi. And of course, its domain is -1 to 1. Now, all right, I'll finish this and then we have to talk about some other details. All right, so I'm just trying to capture what we've done so far. And then the only thing we have left is tangent. All right, we've got, let me see. Yeah, we have to talk about cosecant and secant. That could get a little gross. But tangent, the inverse tangent, this is kind of neat. And remember, this, just to remind you guys, here's what we just did a minute ago. Right? We had to cut it like this. Weehaw! So the inverse tangent, the domain will be the range of this, which is negative infinity to infinity. Jeff, what is that? I don't know. And the range will be the domain of this, which is negative pi over 2 to pi over 2. Do you see any similarities here? Any similarities at all?
There's a positive and a negative.
Okay, I like that. But aren't these basically
They're the same without bracket.
Yeah, exactly. And why does that make sense? Because tangent goes like sine. Why? Because what's on top of tangent is freaking sine. So when sine is big, tangent's big. When sine is small, tangent's small. So it's kind of neat. It kind of goes along. Tangent kind of follows sine because sine is like the dominant function that tangent's based on. All right. So it kind of makes sense. Cotangent has the same kind of stuff going on. So remember, we just did this one. And it was from 0 to pi. So the domain, the range will be 0 to pi. Jeff. Right, because this is the domain of the cotangent. So it becomes the range of the inverse. And the domain is going to be negative infinity to infinity. And again, look at that shit. Look. Look at it. All right, sorry. That's not all right. Now let me see. Let me do this. This is going to be easier. My drawing obviously leaves a lot to be desired. So let's do this. Let's look at the computer generated shit in the book. I'm not going to try to compete with that. Let me find what
Are there? I haven't gotten a chance to watch over the other classes fully yet, but are there cool similarities like that for secant and cosecant as well?
Yeah, we're going to look at that right now. I'm just not going to try to
Okay.
graph them out. Let me see. Does it even have it in here? Oh, do they only do the, wait a minute. Do they only do the 3? All right, I'm a little surprised. Sorry. Yeah, I know I use this book. Give me a break. I can't remember all of it. Jeez. Yeah, they don't even talk about inverse secant yet. Wait a minute. That doesn't make any sense. All right, Jeff. Do strangers in the night. Let's see. Where? No, they don't. Okay, that's strange. Well, they don't even talk about inverse cotangent. All right. So, all right. I'm not going to introduce that yet because that doesn't even show up. That's really strange. I kind of want to do it, but I kind of don't want to do it because I don't want to throw more in your brain than you need for a specific section. Obviously, inverse secant and inverse cosecant exist, right? But again, I'm surprised that this section didn't even talk about it. All right. I was hoping they would have the pictures because it would be easier just to show them instead of trying to draw them. But let me just not introduce those yet. They don't even talk about inverse cotangent, but it is interesting to look at because of the analogy I just pointed, the similarity. Okay, how's everybody doing out there? What is the most immediate use of inverse trig functions? Oh, that's right. This is what I want to talk about. Anybody remember? We did a very quick example of what we can use inverse trig functions to do. You guys remember? Hello? No? You're like, dude, if it happened before 3 hours ago, I have no idea. Okay. So let's talk about this real quick. what kind of thing do I put into a sine? Physically, what is it that I put in here?
An angle measurement.
Kick ass. So I put an angle in there, and very often we use theta, but sometimes we use x, but we know it's an angle. It's some representation of an angle. I like it. And what comes out is just the ratio of the sides of a triangle with an angle in it, blah, blah, blah. Something from -1 to 1, right? Everybody with me? So let's call this, don't call it, let's just call it this. Why not? Cool? Everybody with me? So, what is the output for an inverse sine? How do inverse functions relate? What would the output be for an inverse sine?
An angle.
Good. This is an angle. And the input would be the ratio of the sides. So that's true, period. That is true for any inverse function. The input for the function is the output for the inverse. We know this. We know this. That's why logarithms are equal to exponents, because exponents are the input of the original function. Oh, okay, right? Okay. Maybe. So this immediately leads to, what is this angle if this is 3 and this is 7? Well, right?
3/7.
So I can do, no. What is the angle if this is 3 and this is 7? The answer is not 3/7. That's not what the angle is. The ratio is 3/7. This is how I figure out what the hell the angle is. Stay with me. This is really cool. We're about to do one of the coolest things. All right. And you guys are like, I don't know. You don't use the word cool the same way I do, Jeff. I'm like, all right. I understand. Real quick, can anybody do that for me? What do you guys get for that? And again, I might get different answers based on what mode your calculator is in. I think my calculator is
25.4.
25.4. Thank you, randomly British Jordan.
You're welcome.
And I would also accept 0.44 radians, right? So it depends on what mode. So depending on the mode you have your calculator in, when you do an inverse trig function, it will give you an angle in those units. So if you're in degrees, you get degrees. If you're in radians, you get radians. It's amazing. It's amazing. Okay. So yeah, this would be 25.4 degrees or 0.44 radians approximately. All right. So now watch this. Is anybody not cool with this? Anybody not cool with this? Everybody's cool with this is what that means. Okay. So now watch this. If I do this backwards, can you draw a triangle that this represents? Can somebody tell me, first off, what does this physically represent? What does it represent physically? This, what does it represent?
Triangle.
A triangle?
All right, no. You can draw a triangle that represents the ratio that's in there. What does inverse cosine of something represent?
An angle.
An angle, there it is, cool. The same way that a logarithm represents a exponent, right? All right, so let me call this theta. So I can draw a triangle where that's theta. And what would be 4? What would be 11?
4 would be the y.
No, it's cosine. Cosine likes x, right? Is that cool?
Right. Yeah, got it. Yeah,
And 11, of course, would be
the hypotenuse.
hypotenuse. I love it. So then what's the, and then you can throw this in the calculator and figure out what it is, correct? But I'm not going to ask you that question. I don't give a shit what theta is. Here's what I care about. Get out of here, old problem. I want to know what is the tangent of the inverse cosine of 4/11? If I give you this problem, you look at this and you set up the triangle. Now you say, how do I get the tangent of this angle? That's really all this problem becomes. This is an angle that lives in this triangle. Can you tell me what the tangent is now? What do you need to get the tangent? What are you missing to get the tangent?
Why?
You need, because you need this. Sorry, I tried to run away from my dumb joke. So how do I get this side? It was just good old Pythagorean, right? So it'll be 121 minus 16. You guys with me out there? And now you know what the tangent is. So what's this?
Rad 105/4.
Yes. I like it. So when you have a tangent of an inverse trig, that looks disgusting as shit. But I've hopefully built it. You see this and you think angle that lives in a triangle with the ratio specified by cosine. That was a lot of air I just used. All right. So you do this problem. I'm going to erase this whole problem. Here we go. All right, it's gone. All right, you guys take a minute and do this problem. I want the secant of the inverse. What do you got, Jeff? Inverse tangent of 5/2. Yeah. So some side work here. So which side is 5?
The left one.
So the y side. And what side is 2?
The bottom one.
Yes. And then of course, secant is going to be, secant's related to what?
Cosine.
Cosine. So cosine would be 2 over hypotenuse. So secant would be hypotenuse over 2. So I got to figure out what the shit the hypotenuse is. Right, that's easy. Good old Pythagorean. What do you get? Sorry?
Rad 21.
Rad, well, it'd be 25
Yeah, 29.
plus 4. Yeah, 29 over 2. Done. All right, I'm about to write something up here that makes no sense. And you're all like, that's nothing new. Jeff, all right, you ready? Tell me why this makes no sense.
Because you can't tell the sides.
No, all right. You could, but here.
Because the hypotenuse is then smaller than the other
The thing to
side.
remember is the input for inverse cosine must be the output of cosine. And what can the outputs of cosine, what do they have to live between?
1. It's -1 to 1.
Minus 1 to 1. So you cannot have something in here that's bigger than 1, less than -1. But I like the way Jordan put it. If you try to draw this thing, 11 is the x side, the hypotenuse is 9. What the shit? Not gonna happen.
But could that relate to part of the domain that we cut out?
No. Careful. This is dealing with the range of cosine because it's the input of inverse cosine. We didn't do anything to the range of cosine. It's still -1 to 1. So that's what restricts the input of an inverse is the output of the original. So the input here cannot be outside of the range of the original function. And this is above 1. No good.
Okay, that makes more sense. Gotcha.
So should I be able to do this?
Yeah.
Yeah. Does anyone have an idea how to do this? If
Without the calculator?
Huh?
Without a calculator?
Without a calculator, exactly.
Is it 42 over 100?
Yeah, 42 over 100. So 42 over 100, there's my angle, there's my, and then
Oh,
you,
that was clever. I really didn't have any idea.
obviously what I mean is a problem like this, you know what I mean? But anyway, because you can't really do this without without putting in the calculator, I'll give you that. But I meant like in one of these kind of problems. Okay. So now you can do whatever the hell you need to do for whatever's out there. Yeah. This is sort of like, real quick, side note. You guys ever see those signs that say 7% grade ahead when you're driving on the road and it says 7% grade? Has anybody ever seen that?
Yes.
Yes. What does that mean? Does that mean somebody's watching you and you're going to get a grade at the end of your life as to how well you drove? Or
It's the angle.
good. It's related to the angle. It's related to the slope. 7 over 100. So for every 7 that you go up or down, you go 100 forward. That would be a 7% grade. And 7% grade is actually a pretty good steep hill. Okay. All right. Enough of that. So it's kind of related to what we just did. All right.
I think the house I grew up on was a 12%.
Yeah, buddy. I've seen some. I think that's about the steepest I've ever actually experienced. Was it like 11 or 12% grade? That's where you start to see the signs that say runaway truck ramp. And the first time I saw one of those, I was like, what?
Yeah, my dad used to back our fifth wheel down it. He would because it was like a windy hill, and the only way to do it was to back it up. And
Sure.
one day they detached, and it just soared down the hill.
Oh crap. Oh crap. All right. I don't want to think about that when I'm out driving. All right. So that kind of puts a bow on section 8.3. So as always, you got to get in there. Let me know if you have questions. We're just going to do a little bit out of chapter 9, and then I'm going to let us out a little early tonight, unless there's any objections. Don't forget, what are you also doing tomorrow? What are we doing tomorrow?
Not going to class?
Good, we're not going to class. You can sit there online in an empty Zoom room if you want to.
Did you kind of skipped the secant and cosecant thing that you were about to do? That you said you were going to show us on the thing? You were going to just skip it?
Yes, I'm going to skip it for now because I want to show you and have a complete picture, but the book doesn't do it yet for whatever reason. So I don't want to throw too much shit in your brain now. All right. All right. Give me like the only poor little green dude. Come here. Poor little green dude. Can somebody tell me, besides the reciprocal identities, what is the really only identity that we know at the moment?
Cosine squared plus sine squared equals 1?
I like it. Real quick, what is sine squared A plus cosine squared A?
1.
Good. So it doesn't, as long, now, so what's sine squared A plus cosine squared B?
Don't know.
Don't know, kick ass. So when does this work? When the angles are the same. They have to be referencing the same angle. I like it. Because if they're referencing the same angle, then sine and cosine are the y and x piece on the circle. That's why 1 squared to the other squared is 1, because that's the radius of the circle. If I'm talking about two different angles, they don't do that shit. So this won't work. Okay, maybe. All right. So now watch this. This is cool. This is so cool. All right. Please divide both sides by cosine squared. Why, Jeff? Just do it. So do like this. See, I'm dividing both sides by cosine squared. You can go away now. Thank you for your service. Okay. Is everybody cool with what I just did? Right? There is, now real quick, what angle would this not work for? Or actually what, there's an infinite number of angles, but wherever cosine is,
0.
0, I like it. And we're about to see why it's okay though, because it's kind of like, what does this make?
Tangent
Yeah.
squared.
Squared, okay. Plus
1.
1, okay. Equals,
Secant. Squared.
there you go. Hey, we made a new identity. It's a whole new identity. Sorry, I'm getting excited. By the way, real quick, before I get too far, so here's the main one. Here's the one we just grew. How could I make a third? Let's go ahead and finish this. Can you figure out how to make another one? What do I do to make another one?
Divided by sine.
Yes, okay, do it. Make the third one. These are incredibly enough. These are called the Pythagorean. What? Holy shit, Jeff. Pythagorean identities. I can laugh at myself. Well, you can too. Yes, that's right. I'm sorry. I just saw your chat, Bone. You got it. They are Pythagorean identities because they really are just x squared plus y squared equals radius squared. That's all they are. So if you divide by sine squared instead, what are you guys getting?
One.
1.
Cotangent.
Cotangent
Squared.
squared.
Cosecant. Squared.
Do you guys notice this identity, no co-shit? This identity, only co-shit. Do you understand what I'm saying? Co-shit. Right? So this identity has only co stuff in it, and this identity has no co stuff in it. Do you guys understand what I just said? This is a little thing to help you remember these because you have to memorize these for sure. By the way, we're going to build up more identities, and when we get to a certain point, I'll unlock the list of identities, and it clearly shows what you need to memorize and what you don't need to memorize. Okay. All right. Now, I'm going to erase all this, and I want to show you a use for these. They have more than one use, but I want to show you one immediate useful way to use these. Useful way to use them, Jeff. Good Englishing. Thank you. So this guy. If I tell you that sine theta is 1/2. No. Let's make it more interesting. Sine theta is 3/4. And theta is in quadrant 2. And I want to know what cosine theta is. I can use this to figure it out. I really can. I know what sine theta is, right? You throw that shit in. It's just an equation, right? So sine theta is 3/4. So I'm going to throw it in there. I'm going to get 9/16. Now let me show you something kind of cool that we, us cool math people. Let me show you what we do. All right. We put c squared equals 1, so I don't have to write all that shit, right? So I put s squared for sine and c squared for cosine. It kind of gets messed up with secant and cosecant, so we just have to write those out. Too bad. So can you help me? Solve that for c.
Rad 7/4. Oh, I mean.
Yeah, so you get c squared equals 1 minus 9/16. So you get 16/16 minus 9/16. It's going to be 7/16. So you eventually get square root of 7/4. I like it. There's one mistake you made.
Plus minus.
Normally,
It's in quad 2.
quadrant 2 and
And
cosine.
its cosine's negative.
So cosine theta is negative square root of 7/4. So I didn't have to draw a triangle. I didn't have to do Pythagorean, which I actually did Pythagorean because it's built in. This is Pythagorean. I just didn't have to do it separate. Personally, I don't like doing it this way, but it's there. Right? I kind of like the visual way of doing things, but this is there. This is another way to kind of do it. Thankfully, this is not the only use for this, or else I would be very unimpressed. Okay. So you can do the same thing with the other two, the tangent secant one and the cotangent cosecant one. Okay. Oh, let me think. I don't really know what to do from here. Hold on. Let me think. What should I build next? Let me see. I don't want to do anything too freaky that they don't do yet. Oh, let's do this. All right. So this is called being way too busy and not preparing at all. Okay. So okay, good. I'm doing okay. I'm doing fine. So the first thing that section 9.1 does is exactly what we just did, but then it kind of takes a bit of a turn. We want to solve. Let me make sure I don't forget anybody. Yeah, good. Okay, good. We're going to solve. Well, actually, let's do this first. Yeah, let's do this example. I like this. Verify that tangent theta, cosine theta. Oh, this is easy. Oh God, this is too easy. All right, so there was a problem like this on the quiz. It was the bonus problem. Do you guys remember that bonus problem? Anybody look at it?
Yeah.
Okay.
I was going to ask what made mine, like what I did wrong.
Oh, okay, so what you most likely did wrong, I'm trying to verify that this equality is true. What is it that allows me to do something like this? Why am I allowed to do this? This is a property of equality. So when we verify identities, we're trying to show that the equality is true. We are not allowed to do things to both sides. So what we need to do is either work with one side until it is this, the other side until it is that, or work with both sides until they agree with each other. Does everyone understand what I just said? So when I say verify identities, you are not allowed to do things to both sides because you're trying to prove that the equality is true. Yeah, maybe. And that was bonus, so I can do whatever I want to. Ha. Now, this one is not difficult at all. We almost never do this, but this is a really basic one. Normally, if I can't see something else to do, I rewrite everything in terms of sine and cosine. That normally is a last resort. But this one is such a basic one. What do I get if I rewrite? What can I rewrite in terms of sine and cosine? Obviously, this guy. Because everybody else always is. What is tangent theta? What is tangent?
Sine over cosine.
Sine over cosine. And then what happens here?
They cancel.
Cancel, and look. So look what I just did. This is the work. I mean, this is the work. And then your last step is to say, look, I made that look like that, Jeff. That tells me you're done and you got the same thing. You with me? So that was a remarkably easy example of an identity. So let's step it up a little bit. Ooh, yeah, I like it. I feel like I'm being prank phone called. Let's see, somebody's heavy breathing at me. So here, do this one. Well, like. So it's perfectly fine while you're doing your homework to have all the identities we know so far sitting next to you. This one's going to be pretty straightforward, though, I think. Let's see what you guys think. I highly recommend that you do not rewrite everything in terms of sine and cosine. So you're going to see what I mean. You normally actually don't do this immediately. Sometimes it gives you more work. This one's pretty straightforward. Does someone, let's see, what are you guys trying to do out there?
Multiply both sides by secant squared. Or yeah.
You've earned major pouty face from Jeff, man. So what's wrong with that? Anybody?
You can't multiply both sides by something.
You can't do something to both sides of something that you haven't established is an actual equation yet. So the idea of doing something to both sides is a property of equality. So if you do that, you're assuming it's true. Okay, so we have to pick a side and work with it. You can actually work with both sides if you want to, but obviously which side has got more shit going on? This one. So what are you gonna say?
Isn't secant squared theta minus 1 tangent squared theta?
All right, so we got our sine squared plus cosine squared is 1. We have our tangent squared plus 1 equals secant squared, right? So what's secant squared now? So secant squared minus 1 is tangent squared. I like it. Now there's another way to do this problem, but let's try this way first. All right. So if I do secant squared minus 1 is tangent squared. All right, what do I do from there?
You could make it in terms of tangent on the bottom.
Oh my God, that would so suck.
It's just the same thing.
No. So now you have to break things down. Now, why does this really make sense? What is this supposed to equal? Isn't it supposed to equal sine squared theta? So doesn't it make sense that part of it's going to be sine squared theta? Divided by what's secant squared? 1 over. Yes? Yes? No? What happens to the over cosine squares?
Cancel.
They cancel. Yeah. Now, personally, here's how I would have done this. There's not a damn thing wrong with that, but here's what I was thinking. Or did somebody else do this differently?
Yes.
How'd
I separated like 1 minus.
Good. So this
Oh.
divided by this is 1. 1 over secant squared is
1 over 1. 1 over 1 over cosine.
no, I'm not doing all that shit. It's just cosine squared, right?
Oh yeah.
And then what's 1 minus cosine squared?
Sine.
Check. Okay. So I this is very exciting for me, which I have no idea how you feel about this. This is the first real math thing that you're doing that requires you to play. Right? There have been places before that you could have just played with shit, but depends on who your teacher was, and it depends on how comfortable you were with stuff. Just play with shit. Here, it's almost a requirement of the problem that you play. You try something. And what is going to happen? Something you try won't work. That is also a part of this. So if something you try doesn't work, don't go, oh, what's wrong with me? Go, oh, I'm doing this right because I'm supposed to have something that doesn't work. So let me try something else. I don't know if you guys, so this is where you just try something. There's so many identities we're going to learn. Some of them will be helpful and some of them won't. You'll try something and you go, that's not getting me anywhere. Let me back up. Maybe I play with the other side and do some shit. Maybe I try a different identity. I don't know. So this is like the first thing that says, all right, maybe you've never played with math before. Now you have to. That's why I love it. You would, Jeff. You would love something like trigonometric identities and not even be able to say it. All right, give me a break. I'm tired. All right. So the last thing I want to talk about tonight, we're going to get deeper into, what are you trying to say, Jeff? Trig identities. Oh, yeah. All right. Well, no, let's not do that. Oh, all right. So not too freaky. Hold on. I'm trying to get a good example here of something you're going to see. Okay. No. All right, let's do this one. Okay. I like. So you're gonna have trig identities. We're obviously, man, am I drunk? I haven't drank anything today. We're gonna have trig identities. But we're gonna have stuff like this too. Let's see what you guys think about this. I want you to factor this. So, what did us cool math people do when we saw cosine? What did we replace it with?
C.
C. Now, doesn't that look like a normal thing to factor, right? All right, so how do you factor this?
To C. C. Minus
Yeah.
plus.
2C has to be positive and the 1C has to be negative. I like it. I didn't need all the stupid master product, whatever the shit you call it, because it's 2 and 1. Ain't much going on. So really, what's the answer then? Don't stop here. All right, that's the answer. Now, later, we're going to have an equation that we have to do. right? So that's kind of like, we're not there yet. But this would be a first step in, if this was an equation, well, it would be 0, really, but you get the idea. It would be an equation that we would factor, and then we can solve the equation by studying each of these. So we're building our way up there. That's why this is kind of showing up. It's not just math people going, oh yeah, we got factoring and we got trig. Let's put those together just for fun. No, they show up in equations all the damn time. Okay, all right. That's pretty good. That's pretty good for an intro. So what we're gonna do next week is gonna be, well, obviously Monday we're gonna have our quiz on chapter 8.
Thought you moved it to Tuesday.
Tuesday, that's right, I did. Tuesday. So next week I'll have a quiz on the Tuesday. I gotta remind myself about that. What was I gonna say also? Oh guys, I am so tired. I'm sure you can relate. That's it. That's the word. But this next week is going to be identity craziness, and we're going to do. Oh my god, dude! This probably makes you very scared when I say this, but we're going to do some really cool shit. This is what I told you. Trig functions are ratios of sides of a right triangle. Correct? That's all they are. And we're going to be blown away by all the shit that we can do with them. It's going to be insane. So we're going to do one of my most favorite things ever that requires, if I was in the classroom, I have like 3 separate overhead things that I do. It's something to look forward to. Yeah, Jeff, that is not making me feel scared in any sense at all. Don't feel scared. All right. But I think that's enough for tonight. Can you put the camera up a bit? I'm sorry. That's enough for tonight. So let me know if you need to hang out. Otherwise, you are free to go.
I do have another homework question.
Okay, what's up?
I'm trying to figure out, I got to number 24 on section 8.1, and it's like a picture of a function and like telling what the amplitude, period, midline, and equation is. So
Okay.
I got the amplitude, midline. The period is what I'm a little confused about because it
All right.
doesn't,
So,
it's asking for cosine, but it doesn't start like cosine.
sure it does. Cosine starts at its maximum. That's exactly what it's doing.
I mean, the picture they showed us starts at negative pi over 2.
Oh, no. I mean, so what? So when I say start, I mean at 0. So normally we think 0 to 2 pi. That's how I kind of built the base, the heart of the functions.
Sure.
So yeah, it starts maximally at 0. And of course, it goes infinitely in both directions. So that could actually give me a snapshot anywhere in that infinite. So,
Okay.
big deal. It starts here. Who cares? What matters is this is a non-shifted. It's not been shifted left or right because it's got its maximal point at 0. So I know it hasn't been shifted left or right. So you got the amplitude. What'd you get for the amplitude?
3.
Good. That means you have to know what the midline is.
Negative 1.
Okay. So your only problem is the period. All right. So now watch this. Here's how you do the period for any periodic function, which trig functions are just one example of periodic functions.
Mm-hmm.
I would pick a point like 0 because it's nice and easy. See how this is where, so right before 0, so let's talk about right here. It's going up and then it's flat and then it's going down. Where is the next place it does exactly that at that position?
Pi.
There. So the period is pi. That's how long it takes until it's doing the exact same thing at the exact same place.
Until it begins to repeat.
Yeah. And then it's just the same picture repeating over and over. Yeah.
So how does the period relate to the equation? Is it just the...
So, we know this has not been shifted. This has definitely been shifted down. You with me? And it's definitely got a new amplitude. So it would be A cosine kx. It hasn't been shifted left or right. So that's why it doesn't have like extra shit inside, right?
Yeah.
And then, but it's got definitely got something out here.
Yeah.
I don't know
So
why.
is the k the period related part?
Yes. So the period is 2 pi over k. So now you can actually just k is 2 pi over the period, right?
Which is half? No, that was 4. This one's my brain.
Yeah, the period was
Pi.
pi. So what's k then?
2.
2. Sweet.
Okay, cool.
Very
Okay.
good. Good shit.
I have a question.
Yes.
My question is for quiz 6, the bonus section.
All right. Jordan, is this good? You got what you need?
Yes, I'm good, thank you.
Okay, which so bonus section, okay. Let me see. Quiz 6. Where are you, quiz 6? There you are. Oh wait, let me is it something did you try it and you got it wrong or something?
Yeah.
Okay, let me look at your quiz then.
All right, later.
You, Jordan. There you are. Oh, yeah, so that's what I was talking about earlier. You're not allowed to do something to both sides. So you multiply both sides, you're not allowed to. Yeah. And you can say, well, that's not fair. I didn't know, but it's bonus, so I don't care. I can do whatever I want to.
Oh yeah, but do you work on the both side or?
You can. You don't have to. I would just work with one side until it looks like the other side. But you could work with both sides, sure, but you can't do something to both sides because then you're assuming that the equality is true.
So like I got tangent x times sine x on the left side. Does it equal to?
Tangent x, wait.
It's not.
Oh, I see. Well, no, what's wrong with what you did? There's nothing wrong with what you did. So right where you have sine squared over cosine,
Yeah.
what's sine squared? Isn't that 1 minus cosine squared?
Oh.
And then you can just split it up. Yeah, then you're
Yeah.
golden.
Okay. Thanks.
Cool.
Thank you.
You're welcome.
Have a
Charles,
good-
you doing all right? Kurt, you guys all right?
Yeah. Just had a quick question. It appears I missed an entire question on the quiz.
I think I remember that. Okay, so I mean, you can certainly do it in your corrections.
I because I missed it, I can't see where to see what the question is.
Oh wait, so you can't. All right, hold on. So you can't open the quiz right now? Is that what you're saying?
Yeah.
Okay. Thanks for letting me know. I thought I had done this, but I guess not. There's a button I got to push that lets you see it after you've done it. Hold on, let me push that button, and then. Oh, this is so annoying. All right. There. What happened? I know I pushed that button. All right, so can you try again now? Maybe refresh it.
There's quiz 5.
Quiz 6. Or quiz 5? Do you need?
No. So I'm in unit. So unit 5, unit 6, unit 7.
No. You go to the quiz module. What's happening? Yeah,
I'm sorry.
that's all right.
There we go. Found it.
And I'll
There it
make
is.
sure that opens. I think I pushed the right button this time.
Son of a bitch.
So you're right. It wouldn't open before because it wasn't clicked. I didn't have the little box checked that lets students. Yeah. Okay. So now you can make.
Thank you.
All right. I'll see you later then.
Yes, sir. Bye.
All right.